Hello and welcome to Rest in Science. Tonight, as you settle into a comfortable position and allow the tensions of the day to gently drift away, we're going to embark on a peaceful journey through our cosmic home, the Milky Way Galaxy. Let your breathing slow and deepen as we explore the magnificent spiral of stars, gas, and mystery that cradles our small blue planet. There's no need to focus too intently on every word. Simply let the vast beauty of our galaxy wash over you like gentle waves, carrying you toward a deep and restful sleep. Take a slow breath in, and as you exhale, release any remaining tension from your body. We have all the time in the universe tonight. Our galaxy has been called the Milky Way for thousands of years, a name that carries with it the stories and wonder of countless generations who gazed upward into the night sky. Imagine for a moment ancient peoples across the world, long before electric lights dimmed the stars, looking up at that luminous band stretching across the darkness above them. The name Milky Way comes from the Latin Via Lactea, meaning the road of milk. But this imagery of spilled milk across the heavens appears in cultures around the world. The ancient Greeks told the story of the goddess Hera nursing the infant Heracles, and when he pulled away, her milk sprayed across the sky, creating the glowing path we see tonight. Take a gentle breath and picture this cosmic river of light, this stellar pathway that has guided travelers, inspired poets, and sparked human curiosity since the very beginning of our conscious awareness. Consider how, for most of human history, this band of light was one of the most prominent features of the night sky, a constant companion to our ancestors as they navigated by the stars, told stories around fires, and wondered about their place in the cosmos. Even the word galaxy itself comes from the Greek galaxias, meaning milky, connecting us through language itself to this ancient perception of our cosmic home as a river of light flowing through the darkness of space. The Milky Way stretches across such incomprehensible distances that our minds can barely grasp the true scale of our galactic home. Picture this vast spiral disk measuring approximately 100,000 light-years from edge to edge, a distance so enormous that light itself, traveling at 186,000 miles every single second, would take 100,000 years to cross from one side to the other. Let that settle in your mind for a moment as you breathe slowly and deeply. If you could somehow travel at the speed of light, moving faster than anything with mass can possibly move according to the laws of physics, departing from one edge of our galaxy, you would need to maintain that impossible speed for longer than modern humans have existed on Earth, longer than our species has been painting on cave walls or building civilizations, just to reach the opposite edge. And yet, despite this staggering size, the Milky Way is just one galaxy among hundreds of billions in the observable universe, a single island of stars in an ocean of cosmic islands. The disk of our galaxy is relatively thin compared to its width, measuring only about 1,000 light-years thick through most of its expanse, though it bulges to a thicker middle where ancient stars cluster more densely. Imagine a cosmic dinner plate, vast beyond measure, slowly rotating in the darkness of intergalactic space. And somewhere within it, in one of its spiral arms, about 2/3 of the way from the center, our sun drifts along with billions of companion stars. Within the vast expanse of the Milky Way, between 100 billion and 400 billion stars shine in the darkness, each one a sun. Many with their own planetary systems, their own potential for worlds and wonders we can barely imagine. Take a slow, calming breath and consider the uncertainty in even counting the stars of our own galaxy. We cannot see all of them, cannot catalogue each individual point of light, because vast clouds of gas and dust obscure our view, particularly toward the galactic center where stars crowd together most densely. Astronomers estimate the stellar population by observing the stars they can see, measuring how mass is distributed through the galaxy, and extrapolating outward. But the true number remains wonderfully uncertain, a reminder of how much mystery still surrounds us, even in our own cosmic neighborhood. Each of these stars, whether small red dwarfs that will burn for trillions of years, or massive blue giants that will explode in mere millions, contributes to the great gravitational dance that holds our galaxy together. Some of these stars formed billions of years ago, when the universe was young and the very atoms in your body did not yet exist. Others are being born at this very moment, condensing from clouds of gas and dust in stellar nurseries scattered throughout the galactic disk. And among all these hundreds of billions of suns, our own star is utterly ordinary. A middle-aged yellow dwarf, neither particularly large nor small, neither especially hot nor cool, distinguished only by the fact that it gave rise to us, to consciousness, to beings who can contemplate the galaxy that contains them. Our galaxy is shaped like a grand cosmic spiral, with graceful arms of stars, gas, and dust sweeping outward from a central bulge, creating one of nature's most beautiful and recurring patterns. Breathe deeply and picture these spiral arms, not as fixed, solid structures, but as waves of density moving through the disk of the galaxy, like ripples spreading across a pond. These arms appear brighter than the regions between them, because stars and gas clouds crowd together here. But individual stars constantly move in and out of the arms as they orbit the galactic center, spending some portion of their journey within an arm and some portion in the less dense regions between. The Milky Way has several major spiral arms, including the Perseus arm, the Scutum Centaurus arm, and the Sagittarius arm, each named for the constellation in which we observe them from our vantage point on Earth. Our own sun resides in a smaller partial arm or spur called the Orion arm or local spur, situated between the larger Perseus and Sagittarius arms. Let yourself relax as you imagine floating above the galactic disk, seeing this grand pinwheel structure slowly rotating, the spiral arms trailing behind like water spraying from a cosmic lawn sprinkler, though in reality the rotation is so slow that the sun has completed only about 20 orbits around the galactic center in the entire 4.5 billion year history of our solar system. The spiral structure is thought to be maintained by density waves that travel through the disk, regions where the gravitational pull is slightly stronger, causing gas clouds to compress as they pass through, which triggers the formation of bright, massive, short-lived stars that illuminate the spiral arms like cosmic lighthouses before burning out quickly in astronomical terms. At the very center of the Milky Way lies a region of extraordinary density and mystery, a galactic bulge where stars crowd together far more closely than in the disk where we reside. Take a moment to breathe And imagine this central region, roughly 10,000 light years across, home to some of the oldest stars in the galaxy, ancient suns that formed when the universe was young, when the first generations of stars had only recently begun forging the heavier elements in their cores. These elderly stars orbit in more random, chaotic paths compared to the orderly rotation of stars in the galactic disk, giving the bulge a more spherical shape. The density of stars in this region is difficult to fathom. If we lived on a planet orbiting a star near the galactic center, our night sky would be ablaze with stars so numerous and close that darkness would be almost unknown. Thousands of stars would be brighter than Sirius, the brightest star in our current night sky, and the combined light of all these stellar neighbors would create a perpetual twilight, a sky that never truly darkens. Let your mind rest on this image as your breathing slows. The galactic bulge is also a region of intense gravitational forces and complex dynamics, where the orderly rotation of the disk gives way to a more frenzied stellar dance. Billions of stars bound together in a compact region, each following its own elliptical path around the mysterious center that holds them all in gravitational thrall. This ancient population of stars holds secrets about the early formation of our galaxy, clues written in their chemical composition and orbital patterns, stories billions of years old waiting to be read by patient astronomers. Lurking at the absolute center of our galaxy, at the heart of that dense stellar bulge, lies an object so massive and compact that it defies everyday intuition, a supermassive black hole known to astronomers as Sagittarius A star. Breathe slowly and consider this cosmic giant, containing approximately 4 million times the mass of our Sun, yet compressed into a region smaller than the orbit of Mercury. This black hole is not a cosmic vacuum cleaner pulling everything in the galaxy into oblivion, as popular imagination sometimes suggests, but rather a gravitational anchor around which the entire galaxy rotates. Matter can orbit a black hole quite safely, just as planets orbit the Sun, as long as it maintains sufficient distance and velocity. The gravitational pull of Sagittarius A star is only dangerous in its immediate vicinity, within a few light years of the event horizon, that boundary beyond which nothing, not even light, can escape. We discovered this supermassive black hole not by seeing it directly, which is impossible as black holes emit no light, but by patiently tracking the orbits of stars near the galactic center. Some of these stars whip around an invisible point at tremendous speeds, completing orbits in just a few years, their velocities and paths revealing the presence of an enormous mass concentrated in a tiny region of space. Let yourself relax as you picture these stellar dancers circling the hidden darkness at the heart of our galaxy, some passing so close to the event horizon that relativistic effects become significant, time itself flowing differently for them than for more distant stars. Every large galaxy we observe appears to host a supermassive black hole at its center, suggesting these cosmic giants play an important role in galactic formation and evolution, though the details of that relationship remain an active area of research and wonder. Our Sun, along with all its planets, moons, asteroids, and comets, is not stationary, but rather travels through the galaxy at a staggering speed, orbiting the galactic center at approximately 500,000 miles per hour. Take a deep, calming breath and let that velocity settle in your awareness without alarm. Despite this incredible speed, our solar system takes approximately 225 to 250 million years to complete one full orbit around the galaxy, a period sometimes called a galactic year or cosmic year. Consider that the last time our sun occupied its current position in the galaxy, dinosaurs had not yet evolved. The Earth was in the midst of the Triassic period, when the first dinosaurs were just beginning to appear, when the supercontinent Pangaea still dominated the world, and when the ancestors of mammals were small, unremarkable creatures trying to survive. Since then, Earth has circled the sun hundreds of millions of times. Continents have drifted across the globe. Countless species have arisen and gone extinct. And yet, our solar system has only now returned to roughly the same position in its great galactic orbit. As you breathe slowly and deeply, picture our sun as one traveler among billions, all orbiting the galactic center in a vast, stately dance that has continued for billions of years and will continue for billions more. The sun's orbit is not perfectly circular, but slightly elliptical, and it also bobs up and down relative to the galactic plane, oscillating above and below the midplane with a period of about 64 million years, passing through the densest part of the galactic disk and potentially encountering more dust, gas, and gravitational perturbations during these passages. The stars, gas, and dust that we can observe in the Milky Way, all the visible matter that catches light and reveals itself to our telescopes, accounts for only a small fraction of the galaxy's total mass. Let your breathing slow as you contemplate this mystery. The majority of our galaxy's mass, perhaps 85% or more, consists of something we call dark matter, a substance that neither emits, absorbs, nor reflects light, making it completely invisible to all our electromagnetic observations. We know dark matter exists not because we can see it, but because we can observe its gravitational effects on the matter we can see. Stars in the outer regions of the galaxy orbit faster than they should, based on the gravity of visible matter alone. If only the stars, gas, and dust we observe contributed to the galaxy's gravitational pull, the outer stars should move more slowly, and many should have been flung off into intergalactic space long ago. Instead, they orbit at speeds suggesting the presence of a massive dark matter halo surrounding the galaxy, extending far beyond the visible disk, providing the additional gravity needed to hold everything together. Picture this invisible scaffold, this ghostly framework of dark matter enveloping our galaxy like an enormous, imperceptible cloud, its mass dominating the galaxy's gravitational landscape, even though it remains forever hidden from our view. The nature of dark matter remains one of the great unsolved mysteries in physics. We don't know what particles compose it, how it formed, or why it interacts with ordinary matter only through gravity. As you rest here, breathing gently, consider that the universe is far stranger and more mysterious than our senses can directly perceive, filled with invisible structures and unknown substances that shape the cosmos in ways we're only beginning to understand. The Milky Way is not a static collection of stars frozen in time, but rather a dynamic, living system where matter cycles continuously between different forms, creating an ongoing process of cosmic renewal that has continued for billions of years. Breathe deeply and picture this grand recycling program. Stars form from clouds of gas and dust that collapse under their own gravity, igniting nuclear fusion in their cores when they become dense and hot enough. These stars then spend millions or billions of years converting hydrogen into helium and heavier elements, creating the chemical building blocks of planets and life through nuclear reactions in their interiors. When massive stars exhaust their nuclear fuel, they explode as supernovae, blasting their processed material back into the interstellar medium at tremendous speeds, enriching the gas clouds with elements heavier than hydrogen and helium. These enriched clouds then collapse to form new generations of stars and planets, incorporating the elements created by previous stellar generations. Let yourself relax into this image of cosmic cycling. The atoms in your body, the iron in your blood, the calcium in your bones, the oxygen you're breathing right now. All of these were created inside stars that lived and died before our sun was born. You are quite literally made of stardust, assembled from materials that have cycled through multiple generations of stars over billions of years. The Milky Way currently converts about 1 to 2 solar masses of gas into new stars each year, maintaining a steady rate of star formation that replenishes the stellar population even as older stars fade and die. This balance between star birth and star death, between the enrichment of gas clouds and their collapse into new stars, has shaped our galaxy's evolution and made possible the formation of planets like Earth, rich in the heavy elements necessary for complex chemistry and life. Scattered throughout the galactic disk, particularly in the spiral arms where gas and dust accumulate most densely, lie vast clouds of molecular hydrogen, complex regions of cold gas and dust where new stars are being born at this very moment. Take a slow breath and imagine these stellar nurseries, some so enormous they contain enough material to create hundreds of thousands or even millions of new stars. The Orion Nebula, visible to the naked eye as a fuzzy patch in the sword of Orion the Hunter, is one such nursery located relatively close to us, only about 1,300 light-years away, where we can observe the process of star formation in remarkable detail. Within these clouds, gravity slowly pulls material together, creating denser regions that gradually collapse over millions of years. As a collapsing region grows denser, it fragments into smaller clumps, each destined to become a star or multiple stars if the clump is large enough. The central portions of these clumps heat up as they contract, until eventually the core becomes hot and dense enough to ignite nuclear fusion, and a new star is born, blazing to life in the cosmic darkness. Picture these hidden processes occurring inside dark clouds, invisible to optical telescopes, where protostars slowly accrete mass from their surroundings, surrounded by disks of material from which planets may eventually form. The most massive stars in these nurseries live fast and die young, burning through their fuel in just a few million years and exploding as supernovae that can trigger new waves of star formation in nearby gas clouds, creating a cascade of stellar birth. As you rest here, breathing gently, consider that star formation is not a relic of the distant past, but an ongoing process that at this moment, somewhere in the Milky Way, new suns are igniting for the first time, beginning journeys that may last for billions of years. When you look at the Milky Way on a clear, dark night, far from city lights, you may notice that the luminous band of the galaxy appears to split into two parallel streams in some regions, divided by what seems like a dark river running through the stars. Let your breathing slow as you contemplate this feature, known as the Great Rift or Dark Rift. This apparent gap is not truly empty space, nor is it a region devoid of stars, but rather a vast lane of dense dust and gas that lies between us and the more distant stars of the galaxy, blocking their light and creating the illusion of a starless void. These dust clouds, composed of tiny solid particles made primarily of carbon, silicon, and other elements forged in stars, are cold and dense enough to obscure visible light, though infrared light can penetrate them, allowing astronomers with infrared telescopes to see through the dust and observe what lies beyond. The Great Rift stretches from the constellation Cygnus, the Swan, southward through Aquila and Sagittarius, dividing the summer Milky Way into two streams. Ancient civilizations noticed this dark lane and incorporated it into their mythologies. The Inca of South America saw the dark patches in the Milky Way as constellations in their own right, naming them the serpent, the toad, the baby llama, and other figures, creatures of darkness outlined against the light. Picture these vast dust clouds as cosmic veils, curtains drawn across the galaxy, hiding countless stars from our view while simultaneously serving as the raw material for future star formation. Within the darkest, densest regions of these clouds, gravity is even now pulling material together, beginning the slow process that will eventually give birth to new generations of stars. The interplay of light and shadow, of visible stars and obscuring dust, creates the complex tapestry of the Milky Way as we see it from Earth, a view that is uniquely ours, shaped by our particular location within the galactic disk. Our Sun resides in a relatively calm region of the galaxy, situated in a minor spiral arm called the Orion Spur, or local arm, positioned about 26,000 light-years from the galactic center, roughly 2/3 of the way from the center to the outer edge. Breathe gently and picture our local cosmic neighborhood, a region extending a few hundred light-years in all directions around our Sun, containing thousands of stars, most of them far dimmer and smaller than our own. The nearest star to our Sun is Proxima Centauri, a small red dwarf located about 4.24 light-years away, a distance that light takes more than 4 years to cross. This star has at least one known planet, Proxima Centauri b, orbiting within the star's habitable zone, where liquid water could potentially exist on a planet's surface. Many of the stars visible to the naked eye in our night sky are actually our relatively close neighbors in galactic terms, stars that happen to lie along our line of sight to more distant regions of the galaxy. Sirius, the brightest star in our night sky, is only 8.6 light-years away. Vega, another prominent star of the northern summer sky, lies 25 light-years distant. Let yourself relax as you consider that even these nearby stars are separated from us by distances so vast that with current technology, sending a spacecraft to even the closest would take tens of thousands of years. Our local neighborhood is not a particularly crowded region of the galaxy. The average distance between stars here is several light years, meaning that stars are separated by distances millions of times greater than their own sizes, tiny islands of heat and light in a vast ocean of cold, dark space. This relative isolation has likely been beneficial for the development of life on Earth, as we've avoided close encounters with other stars or their disruptive effects on our solar system's architecture. The visible disk of the Milky Way, the flattened region where most stars and gas clouds reside, is remarkably thin compared to its vast diameter, creating a structure that in profile resembles a pair of fried eggs placed back to back, with thin disks surrounding central bulges. Take a slow, deep breath and picture this geometry. While the disk stretches 100,000 light years from edge to edge, its thickness through most of its extent is only about 1,000 light years, a ratio comparable to a stack of 2 or 3 CDs compared to a large pizza. Our Sun orbits close to the midplane of this disk, oscillating above and below the galactic equator in its journey around the galaxy, currently positioned slightly above the midplane and heading upward, though it will eventually reach a maximum height of about 250 light-years above the disk before gravity pulls it back down again. The thinness of the galactic disk is a consequence of rotation and angular momentum. As the galaxy formed and material contracted under gravity, conservation of angular momentum prevented the material from collapsing in the direction perpendicular to the rotation, creating a flattened structure similar to how pizza dough spreads into a disk when spun. Stars and gas in the disk orbit the galactic center in roughly the same direction, moving on relatively circular paths that keep them confined to this thin layer. Let your mind rest on this image of cosmic order and structure. Not all stars in the galaxy reside in the disk. The galactic halo contains older stars and globular clusters that orbit in more random, elongated paths, creating a roughly spherical distribution around the galaxy. And these stars can venture far above and below the disk plane in their eccentric orbits. But the disk is where the action is, where gas clouds collapse to form new stars, where spiral arms create waves of star formation, where the ongoing evolution of the galaxy primarily occurs. The Milky Way's disk, when viewed edge-on, is not perfectly flat, but rather exhibits a subtle warp, a gentle twisting or bending that becomes more pronounced toward the galaxy's outer edges. Breathe slowly and imagine this cosmic imperfection, this deviation from the ideal flat disk. The exact cause of this warp remains somewhat uncertain, but it's likely related to gravitational interactions with satellite galaxies, or perhaps an asymmetric distribution of dark matter in the galactic halo. Think of a vinyl record that has been slightly bent, no longer lying perfectly flat, but exhibiting a gentle wave or twist. The Milky Way's warp follows a similar pattern, with parts of the outer disk rising above the midplane and other parts dropping below it, creating an S-shaped curve when viewed from the side. This warping affects both the stellar disk and the distribution of gas throughout the outer galaxy, influencing how we see the Milky Way from our vantage point on Earth. For years, astronomers debated whether our galaxy was truly warped, or whether apparent warping was simply a result of our limited perspective from within the disk. Recent three-dimensional maps of the galaxy, created by precisely measuring the distances and motions of thousands of stars, have confirmed that the warp is real, a physical feature of the galactic structure rather than an optical illusion. Let yourself relax into the understanding that even galaxies, these vast cosmic cities of stars, are dynamic, imperfect structures shaped by gravity, motion, and interactions with their surroundings. The warp reminds us that the universe is not composed of ideal geometric forms, but rather of complex, evolving systems that bear the imprints of their histories and their ongoing gravitational interactions with neighboring structures. Orbiting in the halo around our galaxy, distributed in a roughly spherical pattern above, below, and around the galactic disk, are approximately 150 globular clusters, dense spherical collections of stars that rank among the oldest objects in the Milky Way. Take a gentle breath and picture these ancient stellar cities, each containing hundreds of thousands or even millions of stars, packed into a region only a few dozen light years across. In the central regions of a globular cluster, stars crowd together so densely that they may be separated by only light days or light weeks rather than the light years typical of our solar neighborhood. If Earth orbited a star near the center of a globular cluster, the night sky would contain thousands of stars brighter than Venus, and the combined starlight would be sufficient to read by, even at midnight. These clusters formed very early in the galaxy's history, when the universe was young and the Milky Way was still assembling from smaller structures. The stars in globular clusters are ancient, typically 10 billion to 13 billion years old, making them only slightly younger than the universe itself. Let your mind drift as you consider these stellar antiquities, these collections of stars that existed when galaxies were young, when the universe looked very different than it does today, because they formed so early, when the universe contained primarily hydrogen and helium with very few heavier elements. Globular cluster stars are extremely metal poor in astronomical terms, meaning they contain very few elements heavier than helium. This chemical composition provides a fossil record of the early universe, a glimpse into conditions billions of years ago. Globular clusters orbit the galactic center on elongated elliptical paths, plunging through the galactic disk and venturing far above and below it in their journeys. They are not bound to the disk like most stars, but rather belong to the older, more chaotic halo population, remnants of the galaxy's formative era. Astronomers classify the stars in the Milky Way into different populations based on their age, chemical composition, and orbital characteristics, a classification scheme that reveals the galaxy's history and evolution. Breathe deeply and let your mind explore this concept of stellar generations. Population. I-stars, which include our Sun, are relatively young, metal-rich stars found primarily in the galactic disk, especially in the spiral arms where star formation continues today. These stars orbit in roughly circular paths in the galactic plane, moving together like cars on a cosmic highway. Population 2 stars are older, metal-poor stars found primarily in the galactic bulge and halo, including those in globular clusters. These stars formed early in the galaxy's history, before many generations of stars had lived and died to enrich the interstellar medium with heavier elements. Population 2 stars often orbit in more eccentric, tilted paths, creating a more spherical distribution around the galactic center. Some astronomers also refer to an intermediate population of disk stars, intermediate in age and composition, between the young population 1 and ancient population 2. Picture the galaxy as a city with different neighborhoods built at different times. The newer developments, the recently constructed districts, correspond to the young population I-stars, built from materials that have been recycled and enriched many times. The old city center and scattered ancient structures correspond to population 2, built from more primitive materials in the galaxy's youth. Take a gentle breath and imagine this invisible field, somewhat similar to Earth's magnetic field, but on an incomparably larger scale, extending throughout the galactic disk and beyond. The galactic magnetic field is generated and maintained by complex processes involving the motion of ionized gas and plasma, creating a large-scale field that generally aligns with the spiral arms and the rotation of the disk. This field is quite weak by terrestrial standards, thousands to millions of times weaker than a refrigerator magnet. But over the vast scales of the galaxy, it has significant effects. The magnetic field influences how gas clouds move and collapse, playing a role in regulating star formation by providing support against gravity, making it harder for clouds to collapse. It also shapes the paths of cosmic rays, high-energy charged particles that permeate the galaxy, causing them to spiral along magnetic field lines rather than traveling in straight lines. Let your mind drift as you picture charged particles threading their way through the galaxy, following invisible magnetic highways, dancing in spirals around field lines as they traverse vast distances. The galactic magnetic field was first discovered through observations of starlight, which becomes slightly polarized when it passes through dust grains aligned by the magnetic field. More recently, radio observations of pulsars and detailed maps of polarized emission from the galactic plane have revealed the three-dimensional structure of this field. Understanding the galactic magnetic field remains challenging because we can only observe it indirectly through its effects, piecing together its structure from multiple lines of evidence. Our galaxy is pervaded by cosmic rays, high-energy particles, primarily protons and atomic nuclei that speed through space at velocities approaching the speed of light, having been accelerated to enormous energies by violent cosmic events. Breathe slowly and consider these energetic messengers, particles that have traveled potentially thousands of light years, bouncing from magnetic field line to magnetic field line in their journeys through the galaxy. Many cosmic rays originate in supernova explosions, where the tremendous energies involved can accelerate particles to relativistic speeds. Other sources include active galactic nuclei in distant galaxies and possibly even more exotic phenomena we don't fully understand. These high-energy particles constantly bombard the Earth, with millions passing through your body every minute, though at such high energies they typically pass through matter with minimal interaction. When cosmic rays do interact with atoms in Earth's atmosphere, they create cascades of secondary particles, showers of subatomic debris that rain down to the surface. Let yourself relax as you contemplate this invisible cosmic rain, this ongoing bombardment that has continued throughout Earth's history. Cosmic rays may have played a role in the evolution of life on Earth, causing mutations through their interactions with DNA, introducing a source of genetic variation that natural selection could act upon. The flux of cosmic rays varies depending on solar activity and the strength of Earth's magnetic field, both of which help shield us from the most intense radiation. In space, beyond Earth's protective magnetic cocoon and atmosphere, cosmic rays pose a significant radiation hazard for astronauts, one of the many challenges that must be addressed for long-duration space missions. The study of cosmic rays also provides information about the galaxy, as their composition and energy spectrum contain clues about their origins and about conditions in the regions where they were accelerated. By analyzing cosmic rays, astronomers can learn about supernova explosions, pulsar winds, and other extreme environments scattered throughout the Milky Way, places where matter and energy exist in states impossible to recreate in any laboratory on Earth. The Milky Way breathes, in a sense, with gas cycling between the disk and the halo in a process astronomers call the galactic fountain. Take a deep, calming breath and picture this cosmic circulation. Massive stars and supernova explosions in the disk pump energy into the surrounding gas, heating it to extremely high temperatures and driving it upward, away from the disk plane. This hot gas rises into the halo, carrying with it metals and energy from stellar processes, ascending like a thermal updraft, expanding and cooling as it climbs. Eventually, having lost its energy to the cold of intergalactic space, this gas cools and condenses, falling back down onto the disk under the pull of gravity, raining down like precipitation to join the interstellar medium once more. This cycling process helps regulate star formation in the galaxy, removing gas temporarily from the disk where it might otherwise collapse to form stars, then returning it later enriched with heavy elements from the stellar processes that drove it upward. Let your mind rest on this image of galactic breathing, this great circulation of matter between disk and halo. The fountain is not uniform, but rather concentrated in certain regions, particularly where star formation is most active and where supernova explosions are most frequent. Observations of the halo reveal structures of hot, ionized gas and cooler clouds descending back toward the disk, evidence of this ongoing cycle. The timescales involved are vast, with gas taking millions of years to complete its journey from disk to halo and back again. Consider how this process connects different parts of the galaxy, mixing and redistributing matter, spreading the products of stellar nucleosynthesis throughout the galactic system, creating a more homogeneous chemical composition than would exist if gas remained static and isolated in separate regions. The Milky Way has grown over billions of years, not just through internal processes of star formation, but also by consuming smaller galaxies that ventured too close, tearing them apart through tidal forces and incorporating their stars into the galactic halo. Breathe slowly and imagine this process of galactic cannibalism, a slow-motion collision and merger that unfolds over hundreds of millions of years. When a small satellite galaxy approaches the Milky Way, the differential gravitational pull across the satellite, stronger on the near side and weaker on the far side, stretches it into an elongated shape. Over time, this tidal stretching pulls stars from the satellite, creating long streams of stars that trace the satellite's orbit around the Milky Way. These stellar streams wrap around our galaxy like ribbons, marking the paths of now destroyed smaller galaxies. The Sagittarius dwarf elliptical galaxy is currently being torn apart by the Milky Way, its stars spread into a stream that loops around our galaxy multiple times. Let yourself relax as you picture these stellar streams, these fossil rivers of stars marking ancient mergers, each stream a memorial to a small galaxy that no longer exists as a distinct entity. By mapping these streams and analyzing the properties of their member stars, astronomers can reconstruct the Milky Way's merger history, understanding which smaller galaxies were consumed and when. This process of galactic growth through mergers is thought to be common in the universe, with large galaxies building up their mass over cosmic time by accreting smaller neighbors. The stars from these disrupted satellites now orbit in the Milky Way's halo, indistinguishable in many ways from stars born within our galaxy, but carrying in their chemistry and their orbital properties the signatures of their foreign origins, travelers from distant places now adopted as citizens of our cosmic home. Extending far beyond the visible disk and bulge of the Milky Way, reaching perhaps hundreds of thousands of light years from the galactic center, lies an enormous halo of dark matter, invisible yet dominating the galaxy's total mass and gravitational field. Take a gentle breath and contemplate this vast, unseen structure. While the visible galaxy ends fairly abruptly at a radius of about 50,000 light-years, the dark matter halo continues much farther, creating a gravitational well in which the visible galaxy sits like a marble in a bowl. The exact size, shape, and mass distribution of the dark matter halo remain uncertain, as dark matter reveals itself only through its gravitational effects, never through direct observation. Computer simulations of galaxy formation in a universe dominated by dark matter suggest that dark matter halos should contain substructure, smaller clumps of dark matter orbiting within the larger halo, remnants of the hierarchical assembly process through which galaxies form. Let your mind drift through this invisible realm, this dark matter domain that surrounds and interpenetrates the visible galaxy. Some scientists have proposed that dark matter might interact with itself through forces other than gravity, weak interactions that could affect the distribution and structure of dark matter halos. Others have suggested that our understanding of gravity itself might be incomplete, and that what we attribute to dark matter might actually be a manifestation of modified gravitational laws on galactic scales. As you breathe slowly and deeply, consider that the majority of our galaxy's mass is composed of something we don't understand, that the universe holds mysteries far deeper than what our senses can perceive, and that the stars and gas we observe are just the visible tip of a much larger, mostly hidden structure. You need to add some text for me to talk. Understanding the nature and distribution of dark matter remains one of the most important unsolved problems in astrophysics, a puzzle that challenges our understanding of the universe at its most fundamental level. Scattered throughout the halo above and below the galactic disk are mysterious structures called high-velocity clouds, concentrations of neutral hydrogen gas moving at velocities that differ significantly from the orderly rotation of the disk. Breathe gently and picture these wayward clouds, fragments of gas hurtling through the halo, some falling toward the disk, others departing from it, each following its own peculiar trajectory through the galaxy's gravitational field. These clouds were first discovered through radio observations of the 21-centimeter emission line of neutral hydrogen, which revealed gas moving at unexpected velocities, sometimes several hundred kilometers per second, relative to the local standard of rest. The origins of high-velocity clouds remain somewhat mysterious and lightly diverse. Some may be gas expelled from the disk by supernova explosions and stellar winds, now falling back as part of the galactic fountain. Others might be primordial gas left over from the galaxy's formation, never fully incorporated into the disk, orbiting in the halo for billions of years. Still others could be gas stripped from satellite galaxies as they orbit the Milky Way, torn away by tidal forces and now traveling independently. Let yourself relax as you consider these cosmic clouds, some containing enough gas to form millions of stars if they were dense enough, drifting through the galactic halo on their complex journeys. When high-velocity clouds collide with the galactic disk, their impacts can trigger new episodes of star formation, compressing the disk gas and initiating gravitational collapse. Thus, these clouds contribute to the ongoing evolution of the galaxy, delivering fresh gas to the disk and stirring up the interstellar medium. The study of high-velocity clouds provides insights into the circulation of gas in and around the galaxy, the processes that move matter between different galactic components, and the ongoing accretion of material that helps fuel continued star formation in the disk. Hidden among the billions of stars in the Milky Way are extremely ancient objects, stars that formed when the universe was less than 1 billion years old. Cosmic fossils whose chemistry preserves information about the early universe and the first generations of stars. Take a slow breath and imagine these stellar ancients, stars that have witnessed the entire history of our galaxy, that already existed when the Milky Way was young and still assembling from smaller structures. These metal-poor stars, some with less than 1/10,000th the iron content of the Sun, formed from gas that had been enriched by only a few previous generations of stars, or possibly from gas enriched by just a single supernova. By studying the chemical compositions of these ancient stars, astronomers can learn about the properties of the very first stars in the universe, massive short-lived objects that have long since died and cannot be directly observed. The abundance patterns of elements in metal-poor stars carry the signatures of the supernova explosions that enrich the gas from which they formed, allowing astronomers to work backward and infer what the first stars were like. Let your mind rest on the idea that some stars in our galaxy are nearly as old as the universe itself, having formed when the cosmos was young, when galaxies were smaller and more chaotic, when the universe looked very different than it does today. Finding these ancient stars is challenging because they're typically faint, low-mass objects that don't stand out from the crowd. Astronomers search for them by conducting spectroscopic surveys of thousands or millions of stars, looking for the characteristic signatures of extremely low metal content that mark ancient origins. Each discovery of an ultra-metal-poor star is like finding a time capsule, a messenger from the early universe carrying information about cosmic conditions billions of years ago, information encoded in the star's atmospheric chemistry, and waiting patiently to be decoded. When astronomers measure how fast stars and gas orbit at different distances from the galactic center, they find something puzzling and profound. Breathe deeply and consider this cosmic mystery. Based on the distribution of visible matter, stars, gas, and dust, we would expect orbital velocities to decrease with distance from the center, following Kepler's laws, just as planets in the solar system orbit more slowly the farther they are from the sun. But observations reveal something different. The rotation velocity remains roughly constant, or even increases slightly with distance, creating what astronomers call a flat rotation curve. This discrepancy between expected and observed velocities is one of the strongest pieces of evidence for dark matter. To explain the observed rotation curve, the galaxy must contain far more mass than we can see, mass that extends well beyond the visible disk and provides the additional gravity needed to keep outer stars moving as fast as they do. Let yourself relax as you contemplate what this means. The universe is not as it appears. The stars and gas we observe are not the whole story, perhaps not even the majority of the story. Invisible mass dominates the dynamics of galaxies, shaping their rotation, influencing their evolution, holding them together when visible matter alone would be insufficient. The Milky Way's rotation curve has been measured using observations of many different traces: stars at various distances, gas clouds emitting radio waves, satellite galaxies orbiting in the halo. Each method providing data points that collectively reveal the mystery. This flat rotation curve is not unique to the Milky Way, but appears to be a universal feature of spiral galaxies, suggesting that whatever explains it, whether dark matter or modified gravity or something else entirely, is a fundamental aspect of how galaxies work. As you breathe slowly, consider that solving this mystery would revolutionize our understanding of the universe. Answering questions about the nature of matter, the structure of the cosmos, and the laws that govern celestial mechanics on the largest scales. Near the galactic center, within a region extending a few hundred light years from the very core, lies an extraordinary concentration of dense molecular gas, a vast reservoir containing about 10% of all the molecular gas in the entire galaxy, compressed into a tiny fraction of the galactic volume. Take a gentle breath and picture this central molecular zone, a cosmic pressure cooker, where gas densities far exceed those found in most of the galactic disk. The conditions here are extreme by the standards of star-forming regions elsewhere in the galaxy, with higher temperatures, stronger radiation fields, more intense magnetic fields, and more frequent shocks from supernova explosions and stellar winds. One might expect such conditions to produce prodigious star formation, and yet the central molecular zone appears to be relatively inefficient at making stars compared to dense clouds in the disk, producing fewer stars per unit mass of gas than would be expected. Let your mind drift as you consider this paradox. Perhaps the gas is too hot, too turbulent, or too strongly magnetic to collapse easily under gravity. Perhaps tidal forces from the galactic center's strong gravitational field disrupt clouds before they can form stars. Or perhaps our understanding of star formation, derived primarily from studying disk clouds, simply doesn't apply in this extreme environment. The central molecular zone is also chemically distinct, enriched in certain molecules and showing unusual abundance ratios compared to disk clouds. Observations have detected complex organic molecules in this region, suggesting that even in this harsh environment, the chemistry of carbon-based compounds proceeds actively. As you rest here, breathing slowly, consider that the galactic center region is a unique laboratory for studying physics and chemistry under extreme conditions. Conditions that might be more representative of galaxies in the distant past, when the universe was younger, denser, and more violent than it is today. Understanding why star formation is suppressed in the central molecular zone, despite the abundance of gas, may provide insights into what regulates star formation in galaxies more generally. At the center of the Milky Way, the stars of the bulge are not distributed in a simple spherical or elliptical shape, but rather form an elongated bar-like structure, a feature that distinguishes barred spiral galaxies from regular spirals. Breathe gently and imagine this central bar, a cigar-shaped distribution of stars extending perhaps 10,000 to 15,000 light-years from end to end, rotating as a rigid body, all its stars orbiting together while maintaining their relative positions. This bar is oriented at an angle to the line between the Sun and the galactic center, probably about 25 to 30 degrees. The existence of the bar was confirmed relatively recently because we view it from within the galactic disk, making its structure difficult to discern. Only through careful analysis of stellar motions, infrared observations that penetrate the dust obscuring the galactic center, and detailed modeling of stellar dynamics did astronomers piece together evidence for the bar's existence. Let yourself relax as you consider what the bar means for the galaxy's evolution. Bars form naturally in disk galaxies through gravitational instabilities, and once formed, they influence the flow of gas throughout the inner galaxy, funneling gas inward toward the center where it can fuel star formation or feed the central black hole. The bar also affects stellar orbits, trapping some stars into resonant orbits that maintain specific relationships with the bar's rotation. Stars caught in these resonances orbit the galaxy in patterns more complex than simple circles, creating intricate orbital architectures shaped by the bar's gravitational influence. Our Sun, fortunately, lies far enough from the galactic center that the bar's influence on our orbit is minimal, though its presence does affect the overall gravitational potential through which we move. The bar's rotation period is uncertain, but probably around 200 million years, meaning it rotates somewhat faster than the disk at the Sun's distance. Picture this central bar, this elongated structure of billions of stars, all marching together in their grand rotation around the galactic core, a cosmic clock measuring out the centuries in its patient turning. Throughout the Milky Way, particularly in the spiral arms where gas and dust accumulate, stars often form not in isolation, but in groups, creating stellar associations and clusters ranging from loose groupings of a few dozen stars to dense clusters containing hundreds of thousands of stellar siblings. Take a slow breath and imagine these stellar nurseries, regions where a single large gas cloud has fragmented into many pieces, each collapsing to form a star. All the stars in the cluster born from the same parent cloud within a relatively short time, making them siblings of similar age and initial composition. Open clusters, also called galactic clusters, are loosely bound groupings of stars found in the disk, typically containing a few hundred to a few thousand members. These clusters gradually dissolve over time as gravitational interactions between cluster members and encounters with passing field stars slowly evaporate stars from the cluster until eventually, over hundreds of millions of years, the cluster disperses completely, its member stars scattered throughout the galaxy, but forever carrying the chemical signature of their common origin. The Pleiades, visible to the naked eye as a small dipper-shaped group of bright stars, is a famous example of a young open cluster containing several hundred stars that formed only about 100 million years ago and still remain loosely associated. Let your mind relax as you picture these stellar families bound together by the gentle pull of their mutual gravity, drifting together through the galaxy. Globular clusters, in contrast, are much larger and more tightly bound, containing hundreds of thousands or millions of stars in compact spherical distributions. These ancient objects formed early in the galaxy's history and have survived intact through billions of years, their large masses and high stellar densities providing enough self-gravity to resist tidal disruption. Our Sun was probably born in a cluster, though its siblings have long since dispersed and are now scattered throughout the disk, indistinguishable from other field stars, except through detailed chemical analysis that might reveal shared abundances. Between the stars of the Milky Way lies not empty vacuum, but rather a tenuous medium of gas and dust, a dilute ocean of matter through which starlight travels and within which new stars are born. Breathe slowly and consider this interstellar medium, incredibly rarefied by terrestrial standards, with typical densities of only a few atoms per cubic centimeter in the diffuse regions, yet collectively containing billions of solar masses of material spread throughout the galactic disk. The interstellar medium exists in multiple phases with very different properties. Cold molecular clouds, dense and dark, have temperatures of only 10 to 20 degrees above absolute zero and densities of thousands or millions of molecules per cubic centimeter. Warm neutral regions where hydrogen exists primarily as neutral atoms rather than molecules have temperatures of several thousand degrees and much lower densities. Hot ionized regions, heated by radiation from nearby massive stars or by supernova shocks, reach temperatures of millions of degrees but are extremely rarefied. Let yourself relax as you picture this complex, multi-phase medium, with regions of different temperature and density existing side by side, separated by thin transition zones. The interstellar medium is not static, but constantly in motion, stirred by stellar winds, supernova explosions, and the gravitational pull of spiral arms. Shock waves propagate through the medium, compressing gas and potentially triggering new episodes of star formation. The dust mixed with the gas, tiny solid particles of carbon, silicon compounds, and other materials, makes up only about 1% of the interstellar medium's mass, but plays a crucial role, absorbing starlight and re-radiating it at infrared wavelengths, catalyzing chemical reactions on grain surfaces, and providing the seeds around which molecules can form. As you breathe gently, consider that the atoms and molecules in the air you're breathing right now, in your body, in everything around you, once drifted in the interstellar medium, part of this cosmic ocean of matter, before being incorporated into the solar nebula from which Earth formed. Scattered throughout the Milky Way are the remnants of supernova explosions, expanding shells of gas and debris marking the locations where massive stars ended their lives in spectacular cosmic detonations. Take a deep breath and imagine these supernova remnants, some still visibly expanding, glowing shells of shocked gas moving outward at thousands of kilometers per second. The Crab Nebula, remnant of a supernova observed by Chinese astronomers in the year 1054 CE, is one of the most famous examples, a tangled web of glowing filaments still expanding from the explosion that created it nearly 1,000 years ago. At the center of the Crab Nebula sits a pulsar, a rapidly spinning neutron star, the collapsed core of the star that exploded, now rotating 30 times per second and beaming radiation across space like a lighthouse. Supernova explosions play crucial roles in the galaxy's ecology and evolution. They inject enormous amounts of energy into the interstellar medium, heating gas, driving winds and fountains, and creating the hot ionized phase of the interstellar medium. They enrich the gas with heavy elements, spreading the products of stellar nucleosynthesis throughout the galaxy, seeding future generations of stars with the materials needed to form planets and life. They trigger new star formation by compressing nearby gas clouds through their expanding shock waves. Let your mind drift as you consider the violent beauty of supernovae, these cosmic phoenixes that die in fire and give birth to new stellar generations from their ashes. Somewhere in the Milky Way, every 50 to 100 years on average, a massive star explodes as a supernova. Though many of these explosions go undetected because they occur in distant parts of the galaxy where dust blocks our view. The last supernova visible to the naked eye in our galaxy was Kepler's supernova in 1604, more than 400 years ago. We are statistically overdue for another nearby supernova, and astronomers watch certain massive stars as supernova candidates, waiting to see which will be the next to explode. When the next galactic supernova occurs, it will be a spectacular event, potentially visible even in daylight, offering unprecedented opportunities to study stellar death up close. Distributed throughout the Milky Way are thousands of pulsars, rapidly spinning neutron stars that beam radiation across space like cosmic lighthouses, their signals sweeping past Earth with extraordinary precision. Breathe gently and picture these exotic objects, the collapsed cores of massive stars that exploded as supernovae, matter so dense that a teaspoonful would weigh billions of tons on Earth. Neutron stars are typically only about 20 kilometers across, roughly the size of a city, yet contain more mass than the Sun, creating gravitational fields so intense that escape velocity at their surfaces approaches a significant fraction of the speed of light. When a neutron star rotates and possesses a strong magnetic field misaligned with its rotation axis, it can produce beams of radio waves that sweep across space with each rotation. If Earth happens to lie in the path of one of these beams, we detect regular pulses of radio emission, sometimes with periods of only milliseconds, timing so precise that pulsars rival atomic clocks in their regularity. Let yourself relax as you consider these cosmic timepieces, some spinning hundreds of times per second, their rotation rates and periods allowing astronomers to test theories of gravity, study matter under extreme conditions, impossible to recreate in any laboratory, and even search for gravitational waves through their effect on pulsar timing. The first pulsar was discovered in 1967 by Jocelyn Bell and her supervisor Anthony Hewish, who initially thought the regular pulses might be signals from an alien civilization before realizing they were observing a new type of astronomical object. Since then, astronomers have discovered thousands of pulsars throughout the galaxy, each one a beacon marking the death site of a massive star. Some pulsars exist in binary systems, orbiting companion stars, and these systems provide natural laboratories for studying relativistic effects and testing general relativity under strong field conditions. And so, dear listener, we complete our journey through the Milky Way, this magnificent spiral of stars, gas, dust, and mystery that has been our cosmic home for all of human history and will continue to cradle our descendants for billions of years to come. As you rest here in the peaceful darkness, let yourself feel connected to this vast structure, this island of hundreds of billions of stars, slowly turning in the cosmic void. Your awareness, the very consciousness through which you're contemplating these cosmic wonders, emerged from matter processed through stellar furnaces over billions of years, assembled through countless cycles of stellar birth and death, organized through physical and chemical processes into structures capable of understanding, wondering, and dreaming about the universe that created them. The Milky Way reminds us that we are part of something far larger than ourselves, that our small planet orbits an ordinary star in an ordinary part of an ordinary galaxy. And yet here we are, capable of mapping that galaxy, understanding its structure and evolution, predicting its future, and marveling at its beauty. Let this knowledge bring not insignificance, but perspective, not loneliness, but connection to the great cosmic processes that have unfolded over billions of years to bring about this moment, this breath, this awareness. As you drift towards sleep, let the vastness of the galaxy hold you. Let its slow rotation carry you. Let its ancient light surround you. You are stardust contemplating stars, atoms organized into awareness, a small part of the cosmos that has awakened to know itself. Rest now in this knowledge, peaceful and secure in your place within the grand spiral of our galactic home, the Milky Way. Thank you for listening in.